Hello everyone and welcome to our Robotics Final project for the fall of 2018. A project summary is essentially we want to develop a 3D robot workspace with obstacles, compute the configuration space of the robot, run a breadth-first search between a selected start and endpoint, and then perform robot arm movement in the workspace from selected start point to the selected endpoint. We created two separate workspaces for this project that the robot could operate in. We measured each of the dimensions of the obstacles in the workspace and brought that data into MATLAB. The imported obstacle workspace can be seen here in MATLAB. As you can see, we have our robot sort of approximated as different cubes, and right now it's alternating between, or it sort of has a nested for loop where with each theta 1 value, it checks all theta 2 values. With all theta 2 values, it checks all theta 3 values. And we're running a collision detection software, so each time it does this, it's checking to see if the points are colliding or if they're good. We collected this data into an A matrix, which gives us essentially a 3D matrix which tells us what points are collision and what points are free space. So as you can see here, we have some collisions, and then we represent this in this graph right here. So essentially all the red marks are where we have collisions. Our green box right there is where our start point or our initial condition of our robot is, and then the sliders is where we pick our final value for where we want our robot to go to. So as you can see, there's even holes in the middle there, and there's our final configuration for where we're trying to get our robot to go. So obviously next we run our breadth-first search. As you can see, those axis values are theta 1, theta 2, and theta 3. On the left, that's a depiction of our free space and our obstacle space in the configuration space. And then on our right, we sort of have the classic depiction that we've seen of our breadth-first search, where you can sort of see the path in there, the red dots. And here's our robot actually performing the operation and going through into the workspace. Again, we overestimated the robot's dimensions so that it wouldn't get close to things, because then we had initially some issues with it hitting stuff, but as you can see, it sort of slides in very nicely, missing all of the obstacles, and takes sort of an interesting path to get to the point that we wanted it to. So we performed a very similar operation with our rounded workspace. Again, the rounded workspace was just there so we wouldn't have to have our back as an obstacle. So as you can see, it's not there. We only have 4 obstacles, including the floor. Again, it's sort of getting the configuration space right here. Our start point that we have is our green box. And again, the red marks are where we've had collisions. And so we can, on the right, select the sliders, and we can choose an endpoint, which will show up as a blue square. We then can perform our exact same operation of running our breadth-first search. As you can see, again, those are theta 1, theta 2, theta 3. On the left, we have our configuration space, and on the right, we have our depiction of our breadth-first search with, as you can see there, sort of faintly, our path that we've picked to go through our shortest distance path. An alternate depiction of the configuration space can be seen here. Essentially, this uses voxels, or sort of cuboids, to represent our configuration space. This is a little bit more accurate visually to what we're actually doing, but in our computation of our program, we use the point method. That's only because the computation time was decreased by that representation, and thus the code ran faster and smoother. But again, it sort of represents the same configuration space and breadth-first search as we mentioned before. And as you can see here, our robot is now performing its operation through the workspace. Again, as we talked about before, we overestimated those cubes around the robot, so it will avoid the obstacles fairly widely, and that's just because we didn't want wires and other things to get caught. And again, we're using our feedback control, our closed-loop feedback control from our potentiometers. So we calibrated our potentiometers so that we knew what theta values corresponded to each voltage value. So we knew exactly where each joint was, and that's where our robot configuration was at any time. So overall, we were very happy with how this project turned out. Our program worked very well. The robot had a few issues with motor resolution, also potentiometers becoming uncalibrated, which occasionally would mess with our results. But as you can see, we got the robot to travel from a start to an endpoint in the shortest distance in each workspace, so we're fairly happy with that. So overall, we'd call this project a success. We were very happy with it, and we learned a lot.